We are here to listen to the defense of Jessica Mejia, and this is a landmark occasion in any academic's life, a time for us to celebrate the successful completion of a difficult and interesting dissertation project. I am Jackie Dixon. I'm the external chair. My job is to just explain the rules and be an outside witness to make sure that the rules are followed. And then I will introduce the committee and then hand it over to the major professor, Jason Gully, to introduce Jessica. So for these dissertation defenses, the candidate will give a summary of their research. Typically that talk is of the order of 40 to 50 minutes. And then there will be a public question activity. Since we're doing this remotely, what I ask is that people use the raise their hand function, and I will call on them in order. And in fact, Teams does a good job of putting the people with hands up in the order that their hand symbol was used. And we'll go through the public questioning. And usually the committee members limit their questions to the next period. So once we're done a public question period, typically 10 or 15 minutes, then we'll take a little break. Everybody can get a cup of coffee. And then we will come back, and it will be then just the committee members who will ask Jessica more technical questions. During that period, the public is still allowed to listen in, but not ask questions at that time. So if you are not on Jessica's committee, your time for asking questions is immediately following her defense presentation. The committee members are, I'm the external chair. Jason Gully is the major professor of Jessica's research. The other two USF professors are Tim Dixon, sitting next to me, and Glenn Thompson. And the external committee member is Matthew Covington from the University of Arkansas. So I think that's all I need to say. I'm going to hand it over to Jason, and everyone enjoy.
All right, it's a lot of pleasure to introduce Jessica. She came to us with a undergraduate degree in physics and a master's degree in geophysics from the University of Alaska Fairbanks, where she did a very quantitative study of links between the hydrology of motion in glaciers in Alaska. And when she first contacted me, she lamented that she did all of this research on glaciers, but didn't really get to do a whole lot of field work, and was hoping that as part of a PhD, she'd get to do some field work. So originally we talked about doing some stuff in the Himalayas, but we got a project funded in Greenland, and Jessica jumped on that and got a PhD in fieldwork operations in addition to data analysis. So Jessica kind of single-handedly ran the USF component of the Greenland field project. She built almost every piece of equipment that went out onto the ice. And when we talk about every piece of equipment, Jessica shipped over 12,000 pounds of equipment to 2 different camps on the Greenland ice sheet, built a number of GPS stations when we got out to Greenland, and a number of data loggers and environmental sensor networks and weather stations and stuff that she built in her very small lab at USF to try to figure out how to make everything work, disassembled everything, packed it up, shipped it off to Greenland, and we put everything up and made it work. Her organizational skills and ability to get stuff done with very little background in doing any of this was phenomenal. So anyway, the data that she got together and has put together is, I think, going to be exceptionally well cited. She's brought a lot of new insight into work on the Greenland ice sheet. The best part and the most exciting part for me is that all of the ideas that Jessica is presenting today are her own. She even brought some of the initial ideas to me, and I told her that they were probably wrong, and then she argued with me and showed me that I was absolutely wrong and she was right. And very excited to and very proud to present Jessica and her defense. So again, you can hold your questions until the end. We're going to go ahead and mute everybody, and we're going to let Jessica take it from here.
Okay, hi everyone. Thank you for coming today to my defense. Let me just share my screen with you all. And thank you for the introduction, Jason. I appreciate it. Welcome. I am going to talk about the work that I've been doing for the last few years in Greenland, studying the hydrology of the Greenland ice sheet. As you all probably know, climate change and resulting sea level rise are some of the greatest threats to us as a global community. And scientists across disciplines have been working together to understand how Earth systems have responded to recent warmings and how they will continue to do so. Global sea level, shown here in millimeters per year, has been increasing since the mid-1990s and is accelerating in response to rising temperatures. Over the same period of time, the Greenland ice sheet has been losing mass. Here it's shown with mass loss in gigatons, which is 8 billion tons of ice, on the right axis, and then on the left axis, and then on the right is this equivalent sea level contribution. The Greenland and Arctic ice sheets contain the most fresh water on Earth's surface, and therefore have the greatest potential to raise global sea levels. For example, if all of the Greenland ice sheet were to melt, global sea levels would rise by over 7 meters. Accordingly, understanding how the Greenland ice sheet loses mass in response to increased temperatures is essential for accurate predictions of future sea level rise. So glaciers and ice sheets gain mass in their accumulation areas, where more snow falls each year than it melts. So this is a net mass gain. Snow will eventually compress into ice and then flow towards lower elevations under the force of gravity by internal deformation of the ice itself. Glaciers lose mass in their ablation area at lower elevations through two processes. The melting of the ice surface, so termed runoff, is the meltwater melted and then which will eventually reach the ocean. And then also dynamically, so through ice discharging icebergs into the ocean wherever the ice sheet or a glacier is in contact with the ocean, or even lakes. This can happen as well. So mass balance is defined as the sum of the mass gains and the mass losses, which is negative. So glaciers and ice sheets will lose mass and contribute to sea level rise when they lose more mass in a given year than they had gained in their accumulation areas. This results in this negative mass balance, and this is how we quantify current and future contributions of glaciers and ice sheets to sea level rise. So my work focuses on mass loss, the mass loss component. And as I said, this occurs in two processes. So there's direct runoff, which is the meltwater produced, and then this ice dynamic calving, which is effect of the rate of the ice sheet flowing towards the water. In recent years, the Greenland ice sheet has been losing mass at an accelerating rate, with ice dynamic contributions used to account for more than half of these mass losses. However, both of these have grown over time, and now surface mass balance and runoff are the dominating contribution to sea level rise. So this means that the Greenland ice sheet is increasing melting in response to rising temperatures at unprecedented rates in recent history. So these two processes of mass loss are treated separately by most current ice sheet models that are used to project future Greenland ice sheet contributions to sea level rise. However, mounting work demonstrates that meltwater reaching the bed of the Greenland ice sheet influences sliding speeds and therefore mass losses. With the significant increase in melting of the Greenland ice sheet observed over the last decade, understanding how these two processes are linked and how they affect overall ice sheet mass losses are essential. So during the 1990s, meltwater wasn't known to reach the bed of the ice sheet, and accordingly, there wasn't thinking that any kind of increasing temperatures were going to be able to affect Greenland's mass loss. So it thought that it was basically immune to warming climate. However, this changed in 2002 when the first observations of meltwater induced speedups of the Greenland ice sheet were published. So meltwater produced on the ice surface, it flows through networks of superglacial streams and channels, and then it will eventually reach crevasses or moulins. So moulins are vertical conduits that penetrate the full ice thickness, basically tunnels in the entire column of the ice sheet that can penetrate up many meters or even kilometers thick. So these features directly connect the surface to the bed of the ice sheet, where meltwater reaching these moulins can affect pressures underneath the glacier in the subglacial drainage system and act as a lubricating effect. So this occurs whenever the subglacial drainage system is pretty in an inefficient kind of state. This means that basically there are just these link cavities that are created on the back of bedrock bumps as the ice is flowing over it. So, and they have a little hydraulic capacity, and this means that any kind of inputs to moulins will be able to really increase pressures at the bed and create this lubricating effect and allow the glacier to slide quickly over the bed. So this is what gave rise to these fears of this runaway acceleration of the ice sheet. In response to these initial observations, a lot of attention of the glaciological community was focused on Greenland, and a lot of funding promoted studies in field work and satellite remote sensing campaigns, with the attention focused on understanding how the Greenland ice sheet was responding to melting. With this work, observations were made of mid-melt season ice deceleration. So the sliding speeds were actually slowing down during the middle of the summer, even though meltwater was still being produced and reaching the bed. So this is a common phenomenon that's well observed on alpine glaciers, and is caused by the development of an efficient subglacial drainage system. So instead of those linked cavities that I talked about, which would obviously still exist, subglacial conduits can form. And if at the beginning of the melt season, you have this acceleration caused by increased pressures, once subglacial conduits form and they can grow in response to these meltwater inputs, they can lower pressures within the subglacial drainage system, basically reducing the lubrication effect, grounding the ice to the bed more, increasing this traction, and then slowing down sliding. So in contrast to the fears of runaway acceleration of the ice sheet, where there are these positive feedbacks where more meltwater reaching the bed means that more sliding will occur. This increased efficiency with the growth of these channels means that sliding could actually slow down in response to increased meltwater inputs, essentially being a negative feedback. So after these observations and arguments, more research was still being conducted in Greenland. Importantly, observations where moulins were instrumented, and Andrews and others actually investigated if the growth of these subglacial channels was responsible for slowing sliding speeds. They found that this actually wasn't necessarily the case. While there was the presence of these subglacial channels that were conducting meltwater, they weren't growing wildly like they do on alpine glaciers where the ice is much thinner, which means that they can stay open a lot longer to create these lower pressures at the bed. Instead, they suggest that it is actually these isolated cavities that are leaking water into the more connected parts of the drainage system. So whenever cavities are isolated and the volume of water is fixed, whenever the cavities contract, when the ice sheet slows down, it creates a lubrication effect at the bed. And if this covers a large area, this can really affect sliding speeds. But once these cavities connect, water is draining out of them, and this effect diminishes, which can produce this observed slowdown. So with this new theory or thinking of what is controlling the slowdowns in Greenland, this fits somewhere in between of this runaway acceleration or this negative feedback, which is the growth of these subglacial conduits. So but however, this is still unresolved and debated within the glaciological community, and is an important point moving forward to understand how the ice sheet will respond to future meltwater inputs. So how will the ice sheet respond? Ice sheet models, which are used to project future contributions. Here this figure shows sea level contribution in millimeters through time. These ice sheet projections were made in 2007, and since then, work has shown that we are following the upper level trend of this. So any kind of work that we do, we're not trying to see if the Greenland ice sheet is going to continue to lose mass. What we're actually trying to see is how much and how fast the Greenland ice sheet is going to contribute to sea level rise. And this is very essential, having these accurate rates of sea level rise through time, especially in the near future and until like 2100 throughout the century, because it really impacts mitigation measures and adaptation techniques that are going to be developed and deployed around the world. So mounting evidence shows the Greenland ice sheet's hydraulic system exerts important controls on ice dynamics and mass loss. However, we need to better understand these processes and how the subglacial drainage system evolves through time and how it interacts with the meltwater inputs coming to the bed before we are going to be able to incorporate these processes in ice sheet models, which is the ultimate goal. So this brings us to my work, where I focus on better understanding these processes. So first, I'm going to talk about how differences of timing and meltwater delivery to the Moulin connected drainage systems affect sliding. Then I'm going to discuss how I'm going to answer the question, do superglacial drainage catchments and Moulin locations vary interannually? And then I'm going to assess what is the relative importance of channelization versus weakly connected cavities in driving these slowdowns within the Greenland ice sheet's drainage system. So first, I investigate spatial and temporal lags in meltwater production. So how does the timing of meltwater delivery to moulins impact ice motion? Many models that investigate the evolution of the subglacial drainage system prescribe coincident meltwater delivery to moulins throughout the entire model domain. So this is the entire ablation area, which is shown on the left. What this is actually saying by prescribing these uniform inputs is that peak moulin water levels should occur at the same time throughout the ablation area, and that there will be uniform lubrication at the bed. So peak sliding will occur at the same time. However, recent observations suggest that this isn't the case. So work by Hoffman and others, where they deployed GPS stations across the ablation area at different elevations, they showed that peak sliding speeds occurred later in the day at their higher elevation sites further from the margin, and earlier in the day closer to the margin at these lower elevation sites. So this is basically showing that this uniform lubrication of the bed is not actually happening. Well, it could not be. So what could be the case for this? It could be the timing of meltwater delivery to these moulins. So an internally drained catchment refers to the area of the ice sheet surface that drains into a terminal moulin. So smaller catchments have a shorter area to drain through before reaching the moulin, so it should occur faster than for larger catchments. And work investigating large areas of the ice sheet show that times between peak meltwater production and delivery to moulins can vary widely over the ablation area, occurring from less than an hour to over 8 hours. And this really contrasts alpine glaciers, which are much smaller and have a lot less heterogeneity. So you don't need to take these same considerations into account. So why were these lags between peak meltwater production and delivery further from the margin? Well, this is because moulin density decreases with distance from the margin. And with a lower moulin density, that means fewer actual point sources of inputs. That means that each moulin will drain a larger catchment area. So you'll have these larger catchments and presumably these longer lag times. So what would the potential implications be? So earlier in the day, if meltwater is delivering, or if meltwater delivery to moulins occurs earlier in the day, then lower on the ice sheet in the ablation area, you should observe peak pressures earlier in the day, and then later in the day, you should observe these peak pressures up glacier. So basically, you have more resistance to flow in these scenarios. And also, this timing could affect the subglacial pressure gradients that are incorporated by these models that govern the evolution of subglacial conduits in the drainage system. So it's an important point to resolve. However, few observations of moulins exist on the ice sheet, even though recent work using them prove that they're essential and it provides very important information to give us insights about the function and behavior of the subglacial drainage system. So in this study, to answer how differences in the timing of meltwater delivery to moulin-connected drainage systems affect sliding, we directly measure moulin water levels and ice motion at 2 different elevations within the Greenland ice sheet ablation area. So we established our field work for this entire study. It's from the Western Greenland ice sheet in Sermiak-Avanyadak, which is in the Pakitsak region of the Greenland ice sheet and right near Ilulissat, on a land terminating portion of the ice sheet. So let me zoom you in. So we established a lower elevation site, low camp, and a higher elevation site, high camp, and we instrumented moulins at both of these sites. So in addition to moulin instrumentation, we installed weather stations and we filled data gaps using the Greenland Climate Network Station JAR 1. We installed stream gauges to measure the timing of peak meltwater delivery to moulins. We instrumented moulins at each site with piezometers to monitor the timing of peak moulin water level. And then we installed an array of GPS stations on the ice to constrain the timing of peak velocities. So here I'm showing you the timing of the propagation of meltwater through the drainage system at our low camp site on the left and our high camp site on the right. So peak melt occurred simultaneously at both camps, as was expected, around the timing of solar noon. At low camp, peak meltwater delivery to the moulin, or peak stream stage, occurred 3 hours after peak melting occurred. At our high camp site, the timing of meltwater delivery to moulins took a lot longer, on average over 6 hours, but in this case 5, which makes sense because our moulin, at High Camp, the drainage basin was around 16 square kilometers, much larger than our smaller catchment at Low Camp that was on the order of 0.2 kilometers. So then the timing of peak Mullen water levels lagged behind peak meltwater delivery by approximately 2 hours at both sites, with no significant difference between the two sites. And then at our Low Camp site, peak sliding occurred around the timing of peak Mullen water level. However, at High Camp, peak sliding lagged behind peak Mullen water level by 5 hours, and altogether lagged significantly. So these observations do show that peak Mullen water level is occurring later at our High Camp site than it is at our Low Camp site. For all of our coincident observations, this lag between Mullen water levels range between 1 and 3.5 hours. So that shows us that the timing of peak pressures are non-uniform across the entire ablation area. Furthermore, the timing of peak Mullen water level and sliding being nearly coincident at our Low Camp site agree with previous observations that show that there's a strong coupling between the two, closer to the ice sheet's margin, and that there are these local controls on sliding. However, at High Camp, we identified some non-local controls on sliding because the timing of peak Mullen water level couldn't fully explain the timing of peak sliding speeds. So how does Mullen density influence the coupling between hydrology and ice dynamics in the Greenland ice sheet? So earlier in the day, where Mullen density is high and meltwater delivery times are shorter, this means that pressures are occurring basically uniformly or with small differences, and the upglacier area is exerting drag and resisting flow. However, at our High Camp field site, these non-local controls could be explained by a higher sensitivity to other nearby catchments that may have even longer lag times between meltwater production and delivery to those Mullens. So peak Mullen water level may occur at one Mullen, but peak sliding speeds might be delayed until a nearby Mullen raises its pressures and is no longer resisting sliding as much. So that may explain the non-local controls that we observe. In summary, with this work, the most important thing to consider is that we shouldn't assume these uniform control or uniform timing of meltwater delivery throughout the entire drainage system, because they can have significant implications for not only the timing of peak pressures in different areas, but we show that the timing of peak Mullen water levels and the pressures in different areas of the bed can actually interact with each other and really influence the coupling between hydrology and sliding, especially at these higher elevation sites further from the ice sheet's margin. Okay, and then going on to my second work, assessing the interannual variability of internally drained catchments. So, as I said before, internally drained catchments are the area that drain into a terminal Mullen. These are usually thought to be static because ice surface topography is largely controlled by the bedrock. So this is transferred to the ice surface as water or as the ice sheet flows over the bed, and can induce significant heterogeneity on large scales. However, in addition to the transfer of bedrock topography to the ice surface, the ice surface is also shaped by the incision of these superglacial streams, because instead of eroding like sediment, in terrestrial system like the Grand Canyon, cutting through rock or carrying and depositing sediment like deltas. On glaciers and ice sheets, heat is actually just melting more of the channel's floor and the boundaries and incising into the ice surface. And this is occurring faster than the rest of the ice surface is ablating and melting downward. So what is the relative importance of this static bedrock topography versus this variable fluvial incision in governing stream routing on scales that are relevant to internally drained catchments? So this is important because the size and location of internally drained catchments and moulins affects the timing of meltwater delivery to the subglacial drainage system, as I just previously demonstrated. So previous works have addressed this issue by using mostly remote sensing techniques. So in this study, they compare predicted superglacial stream flow paths that were calculated using just the large scale topography that is transferred from the bedrock, and they compared this to observations. So here the green shows a match where the streams were actually flowing as predicted, and the red shows a mismatch. So the red is areas where streams are flowing uphill with respect to local topography. So the conclusion was that because for most of the stream's length on the catchment scale, flow is in agreement with this large scale topography, that fluvial incision didn't really matter, and therefore because bedrock topography is static, it's unchanging, internally drained catchment shouldn't change over time. However, there have been observations within the Greenland ablation area of superglacial streams breaching topographic divides. So this means that superglacial streams, them lowering their base level via fluvial incision, can depart significantly from predicted flow paths. Specifically, you would think that if these superglacial streams, if they are diverting from flow along most of their lengths, it probably shouldn't matter. The most important part that we need to think about is the part of the stream, or the highest order, which is the largest part of the stream that is flowing directly into moulins. So if the highest order channel can deviate from this large scale topography, then that could potentially prevent access from the catchment's terminal moulin. And this could change the geometry or locations of internally drained catchments. So here we investigate this by first mapping the highest order superglacial streams in 3 mid-elevation catchments at our high camp site, and to see if they adhere to this large scale topography. And then we use observations as a baseline to compare flow routing during the next melt season. So we focused just on our high camp site. So radical drainage basin here in Moulin was the Moulin that we instrumented during 2017 that I was discussing with when I was discussing lags in the timing between meltwater production and delivery to moulins. And this catchment and stream generally followed large scale topography near the terminal moulin, just shown here, the 2017 flow path. Now moving on to Mars and Arksov catchments and lakes. So each of these had a lake that they were draining. And I'm going to zoom you in here. So in 2017, we mapped these flow paths using the roving GPS setup. So first I'll talk about Mars Lake. So here is that data. So on the right, we have Mars Lake shoreline. And then on the left, we have Mars Terminal Mullen. So this superglacial stream incised a canyon that reached a topographic height of 11 meters, which is pretty significant. Here's just a picture of looking uphill when we were approaching the top of this stream. And then here's a photo of Jason standing there next to this incised canyon of 11 meters deep with all of these collapsed snow bridges, which indicated that at least part of the stream, the superglacial stream, was initially created during a previous melt season by this existing over the winter that would allow these snow bridges to form and then melt out during this melt season. After reaching the topographic high, flow was then in agreement with large-scale topography until we reached Mars Mullen, very large mullen draining the lake with these fresh fluvial features. So then for Arksov, instead of reaching a topographic high and going to the other side, instead Arksov Lake drained into Arksov Mullen, which was just located 3 meters above the shoreline at the time of drainage. But still, so for Arksov Lake, all of the flow was counter to this large-scale topography, and for Mars, it was half of it. But importantly, both of the terminal mullens required this uphill flow for the lakes to be draining into them. And also, Arksov Mullen had a portion of the stream where there was a part of the snow bridge left, a snow bridge. So key points: the deeply incised superglacial channels draining both Mars and Arksov lakes flow uphill with respect to large-scale ice surface topography. This uphill flow allowed lakes to drain into mullens outside of their local drainage basin, and Mars Lake appeared to drain through the same canyon size during a previous melt season. So in 2018, each of the highest order streams identified in 2017 were rerouted during the 2018 melt season, which is shown in blue, resulting in each catchment draining into different terminal mullens. This flow rerouting changed the characteristics of the internally drained catchments to various degrees. First, I will talk about Arksov Lake's flow paths rerouting, and then I will talk about Radical River, which breached this topographic high to flow into Mars Lake. So I'll finish up with that. So zooming in here, Arksov Lake, it followed basically a parallel flow path, but it abandoned the snow-filled stream formed during the previous melt season. So on the bottom, you can see, again, it was flowing uphill with respect to this large-scale topography, but it actually flowed into Mars Mullen in 2018 that Mars no longer flowed into. And then looking at the intersection where the stream diverted flow, it basically turned at a right angle and at the snow plug, and then there are these overflow features there. Yeah, and this shows the 2017 flow path. Okay, so now Radical River. So here is a picture. So on the right, we have the old Radical Mullen, if you can see, and this is the snow-infilled stream that led to Radical Mullen. Radical River on the left-hand side was flowing towards me taking the photo. And at this intersection, there was this slushy interface. So Radical River flowed uphill with respect to local ice surface topography, or with large-scale ice surface topography, reaching this topographic high. These two photos were taken right at the point of this topographic high, right approaching it. And the stream basically was meandering and slowly kind of approached the topographic high. And once it breached the topographic high, it then again followed large-scale topography before emptying into Mars Lake. diverting flow. So zooming into Mars Lake here. So this shows the 2017 flow path filled with snow, and you can see that the water tried to melt it out, but it just didn't get all the way through in 2018 like it did the previous year. Instead, if you see the pink line at the top of the screen to the north of this, the Mars Lake breached a different point on the lake shoreline and incised a new flow path. So why did Mars not reactivate why did Mars not reactivate and melt through that snow plug like it did the previous year? The only significant difference was that in 2018, Mars was actually being filled by now Radical River. So the emptying of this river into the lake would have affected the lake filling rate. So here are some photos just showing. So A is taken right near the shoreline, showing these fresh overflow features where the lake breached this higher elevation area and then incised deeply, similar to what we saw the previous year with these deep incised canyons. B is approaching this topographic high. And then this picture on the bottom, C shows this is taken at this topographic high point right near there, showing these overflow features and deep incision draining the lake. And then finally, after breaching the topographic high, water followed large-scale ice surface topography again, and finally drained into Phobos Moulin to the upper left-hand side of the screen. So what are the consequences of this observed interannual variability in stream flow routing observed? So Moulin location was redirected around 3 kilometers away. At these higher elevations, there's already a low Moulin density, so that was further decreased. Here, I'm going to talk about how this flow was diverted. So first, you have a deeply incised channel. Then over the winter, it will fill with snow. During the subsequent melt season, other areas should melt faster, and the snow plug should take longer to melt because of the higher albedo once other areas are exposed. The ice is exposed in other areas. So water will pool as this water tries to melt through the snow plug. This is especially true. So it will pool right there at the interface as this water is trying to melt through, but it's very inefficient. So it's where surface slopes are shallow, this pool will eventually spill over if it can't melt through the snow plug. And if surface slopes are shallow, this will allow the flow to be diverted away from the terminal Moulin, and the meltwater will incise a new path. And as we showed before, even though these streams are only flowing uphill for short lengths on the overall catchment scale, where this uphill flow affects access to the terminal Moulin, that can significantly affect the size and shape and locations of internally drained catchments. So where should this matter? So a lot of observation, especially closer to the ice sheet's margin, where surface slopes are a lot more steep, which would redirect flow, back towards the same Moulin location. And also Moulin densities are higher, show that there's literal interannual variability. So here we argue that this should really be an important process, mostly at higher elevations where surface slopes are a lot more shallow. And these can promote like this meandering and diversion of flow away from moorlands. Accordingly, future work should not hold these catchments as static in models. Instead, these models can potentially just identify areas with shallow slopes and moorlands nearby and identify these areas as maybe potentially vulnerable to breaching in the future, and then manually remove or remove randomly different moorlands in these vulnerable locations to investigate the results or the effects on like hydrodynamic coupling in the model runs. This would allow prevent you from needing to identify moorlands or identify these processes, which would be very time intensive and hard, and you can't project that into the future. So that would probably be the best route forward. Okay, finally, I'm going to talk about the subglacial drainage system. So rapid superglacial lake drainages trigger Greenland ice sheet slowdowns. So here we focus on data from low camp. And low camp was positioned down glacier from several up glacier superglacial lakes that were known to drain in previous years. And along the same subglacial flow path. So we instrumented the moorland, have some GPS stations that were active, and also a seismometer that was measuring glacial hydraulic tremor and ice quake amplitudes. So here I'm showing you on the top we have our moorland water level time series. Then I have tremor amplitudes in the middle and along flow ice velocity from those two GPS stations. And this is showing us throughout the 2018 melt season or year. So we're about to get to the melt season. So in June, beginning of June, ice was sliding at these wintertime background speeds before meltwater was reaching the bed and could affect any or implement any changes in the structure. Then the melt season began and the ice sheet accelerated as expected. Here I just mark these background sliding speeds. Okay, as the melt season progressed, we see the onset of diurnal velocity variations. Then at the beginning of July, we instrumented our low camp moorland, and we see clear diurnal velocity variations as well as moorland water level variations and variations in tremor amplitude on daily timescales. So this is just showing that daily meltwater inputs are affecting pressures at the bed and sliding speeds. This just shows wherever moorland water levels fall below the sensor in a period where there was rain. That explains the high amplitudes there. But importantly, throughout this time, diurnal minimum velocities were always consistently above winter background speeds, even when the moorland water level fell below the piezometer's level. So on July 25th, we observed a spike in all of our observations that was indicative of a superglacial lake drainage event. So looking at satellite imagery, we see these lakes full before this spike, and then we see them drained after this spike. So these lakes likely drained via hydrofracture, where they will, instead of slowly like we just saw, where they overtop a drainage basin and flow into a moorland. This happens whenever there's a crevasse that forms very close or within the same basin, and then it can this meltwater can hydrofracture the crevasse to the bed and then create this subglacial flood wave that will rapidly flow down glacier. So that's what we captured here. So let's zoom in. Okay, so time is on the x-axis, and then we have our observations here. So we have head, and then we have our uplift and ice velocity time series. And I just showed displacement to constrain the timing of these peak sliding speeds. And then I have tremor amplitude. It tells us when the flood wave arrived at our site. And then on the bottom, I have ice quake amplitude to show when there are ice quakes at the bed. So before the flood wave approached our site, we observed normal diurnal behavior. Then we see a pressure rise ahead of the flood wave and sliding speeds increase. And there's some uplift with these rising pressures. So the yellow bar marks the time of the flood wave is actually under our sites, as is indicated by the tremor amplitude. So we see that the flood wave arrives at our site. Moulin water level peaks with subglacial pressures rising in the moulin instead of rising from superglacial inputs. Water is being pushed up under the moulin. Sliding speeds are increasing. We see this high amplitude tremor. So here we see the flood wave's arrival. Yep, increased sliding speeds, uplift. Yes. And then after the flood wave passes our site, moulin water level is slowly falling. So that means pressures are falling slowly. And by 2 hours later, most of the floodwaters had drained past our site. And we see the onset of these large, deep ice quakes. So after the subglacial flood wave drained past our site, moulin water level declined slowly, and then sliding speeds slowly declined, eventually reaching background speeds. However, at this time, moulin water levels were still extremely high. They were higher than the diurnal maximum values over the previous week, indicating that it wasn't the growth of subglacial conduits, has previously been explained to drive slowdowns in Greenland. We also see that tremor amplitudes were similar to the day before, indicating no significant increase in hydraulic efficiency of the subglacial drainage system. So let's zoom into the period after the event so I can show you what happens. So we initially see that velocity fell to winter background speeds. Then we resume these diurnal variations after the flood wave drained past the site. So this is showing us how the subglacial drainage system may have changed. So after this time, diurnal minimum ice velocities continuously drop to wintertime background speeds at multiple times. Specifically, even at some points when moulin hydraulic head is above the piezometer level, which used to cause sliding speeds to be above background speeds. Now sliding speeds were dropping lower. It's a slight difference, but it's indicating that the change in the ice velocity observed was not being caused by changes in the moulin-connected efficient subglacial drainage system. This change in relationship between diurnal minimum indicates that the lake drainage induced a persistent increase in basal traction, and that this basal traction increase is consistent with the dewatering of isolated cavities because it can't be explained by increased growth of these subglacial channels. So here's a conceptual model of what we think to have occurred. So before the lake drainage, there's a high proportion of isolated cavities at the bed. The flood wave approach, inducing transient connections. Then the flood wave received, allowing these cavities to drain into the more connected drainage system. And at this time, pressures in the most efficient parts of the drainage system would still be high. And then after the flood wave subsides and water starts to drain, water could drain out of these isolated cavities. So what does this mean? This means that rapid lake drainages can influence slowdowns despite not increasing the efficiency of the subglacial drainage system. The shallow slopes and thick ice of the Greenland ice sheet might limit subglacial channels' ability to lower water pressures over a large area of the bed, and reduce pressures in such a way that they can really govern these slowdowns. And accordingly, the Greenland ice sheet would be potentially more vulnerable to sustained meltwater inputs than previously thought, because these isolated cavities don't respond in the same way to meltwater inputs as a channelized drainage system. So there's not necessarily the same negative feedback process in Greenland. So this adds more support to the previous observations that it is these weakly connected areas of the ice sheet that are driving these slowdowns. And hopefully will convince others that channelization, while important and does exist in over large parts of the ice sheet and does adjust to meltwater inputs, they can't be exclusively thought to govern the coupling between hydrology and sliding in the Greenland ice sheet. So in conclusion, for all of this, we basically show by looking at all the superglacial drainage system, these inputs to the Mullen connected subglacial drainage system, that it all works together in that the Greenland ice sheet is very different from alpine glaciers, and we can't just assume that processes observed closer to the Greenland ice sheet's margin or that are well understood for alpine glaciers necessarily are responsible and have the same relationships to sliding on the Greenland ice sheet. So, finishing up references for the figures I use, I would like to thank my committee, my advisor, Jason Gully, for the opportunity for my PhD, and Matthew Covington, who is also works on this Greenland project with us. Also, Tim Dixon, been very valuable, and Glenn Thompson. Also, Len Batcher, he's no longer on my committee, but I've learned a lot from him throughout this process. And I really thank Jackie Dixon for being the chairperson of this defense. I'd also like to thank my co-authors, especially Celia Truntz and Surizi and Tim Bartholomos, for their work and insight into developing a lot of these results. I'd also like to thank the people who help with field work, Celia, Vicky, Charlie, and Ronnie, and Kathy Young and Annie Zano from UNAFCO. But really, I would like to thank Celia. I couldn't have done any of it without her. I really couldn't have. She's been so valuable. And I'm really happy I met her throughout this. I also would like to thank my Glacier Hydrology Reading Group friends and friends at USF, my family, especially my husband, Jorge Mejia. I couldn't have done it without his support and being willing to follow me wherever I get a job next, like here in Alaska and everywhere, and his support through the whole thing. And also my best friend, Kalea, for her help, especially last minute dissertation edits. I appreciate it. Also my parents and the rest of my family. It all means a lot for everyone's support. So you can contact me here, and most of this data is available at the Arctic Data Archive.
All right, let's all say great job, great figures. You can use your clapping hand icon as well. We'll do the clapping hand icon. All right. All right, Jessica, take a breath. Good job. And now for the people attending remotely, If you have a question, use the raise your hand icon, and then I will call on you with questions, and we'll try to keep the committee members, the non-committee members asking questions first. So let's see, do I have any? Normally they will appear. Okay. There was a hand, yes. Lauren Andrews.
Hi, Jessica. Congratulations and thanks for the nice talk that you gave. I'm going to pick from my list of questions I have for you. So I think for your second chapter, you did a nice job of really demonstrating that different internally drained catchments can essentially breach topographic highs. But one thing that I'm wondering about is how important do you consider this process to be? Because there's been a lot of work demonstrating that, at least at the very large scale, the topography, the subglacial topography and ice thickness does a really nice job of dictating superglacial catchments. So do you actually think that if you included this process in a model of superglacial hydrology that you would actually, or glacial hydrology in general, that you would actually expect to see large scale changes in subglacial pressure or ice velocity? Or do you think that this is it's an interesting and potentially impactful component to different or really small regions? So thanks.
Thanks for the question. So I think that this process of drainage basin breaching probably isn't very significant, especially closer to the margin, but especially further away from the ice sheet margin at higher elevations, I think that it can be very significant. So with one of our drainage basin breaching, right, Radical Mullen, that effectively expanded the size of the catchment that used to drain into Mars Lake by more than double, and also the addition of Radical draining into this lake affected the rate of lake filling, which then allowed the lake to probably drain into breach a different topographic high instead of melting through the snow plug like it did the year before. So I think that these can have cascading effects and can really influence subglacial hydrology, especially with the first chapter, my lags chapter. I show that there are these non-local controls on sliding. So especially further from the ice sheet margin, it seems that the timing of pressures in nearby catchments probably has a more significant influence on sliding speeds as a whole. So I think that that's where it's important, and especially because the ablation area continues to extend inland, and it will continue to do so in response to future warming. That means that there's an increasingly larger area where this process could be very important. So while now I guess the area is probably limited with respect to the size of the ablation area, I see in the future that this could actually account for a more significant role.
Great, thanks.
All right, Lauren, did you have another question or shall I move on?
Oh, well, I mean, I can follow that up with, so essentially you have made measurements of superglacial discharge, and you have the superglacial drainage catchments. This is just out of curiosity, have you actually compared your timing with the proposed unit hydrograph parameters by Larry Smith in his 2017 paper? And are they similar or are they different, if you have?
Okay, so I did for Radical catchment, and actually Larry Smith's estimates for my catchment based on the geometry and the factors, those predicted lags in meltwater delivery to be around 2 hours, but we observe it on the scale of 5 to 6 hours, the actual lags of meltwater delivery for that same catchment. So it seems to be double what would be predicted by those simple empirical calibrations.
Any guesses or thoughts on why? Is it geometry? Is it surface characteristics?
I think that it's mostly that they determine their empirical coefficients from a different area and also from a few catchments. I think that could be inherently not applicable to large regions, or it can vary between different catchments, so that you can't be applying that same empirical scaling parameter across the ice sheet.
I will email you further questions. Thanks.
Okay.
Great. Thank you, Lauren. I see a hand up for Charlie.
Yeah, hey Jessica, good job.
Hey.
It was really great.
Thanks.
See all the data kind of come together at the end here. I hadn't seen a lot of those profiles and stuff that you put together. They're super neat. So my question is, so in your first paper, you show that you have this difference in density of moulins, down glacier versus up glacier. And then in the second paper, you show that these snow plugs that are forming in these channels and stuff really end up kind of controlling that surface drainage system by redirecting all of the surface runoff. So do you think that there's some kind of a relationship just between the amount of permanent snowpack that you get further up glacier and the density of moulins that you're going to get? Is that going to kind of control that on top of just the density of crevasses and stuff that you get down glacier?
Yeah, so I think that if I understand your question right, so that's definitely plays a role, because lower on the ice sheet where there are more moulins, even if there is this breaching, the river doesn't have to travel very far to reach another crevasse or moulin. So really, that wouldn't impact the actual location of where meltwater is reaching the bed or the catchment areas, because it doesn't need to go multiple kilometers and go through lakes that have to, breach these other topographic divides before finally following a moulin. So yeah, I think that's definitely an added level of complexity in the superglacial drainage systems.
Cool. Yeah, it was really awesome to see that the profile at the Mars Moulin, just going through that 11 meters. That's pretty crazy. But good job.
Thanks.
All right, I'm not seeing any other hands up. Last call for non-committee member questions. Hearing none, let us once again congratulate Jessica on a job well done. Wait, no more questions. Okay, so let's take a break for 10 minutes. And so we will resume at 2:50 p.m. And we'll just let Jessica take a breath, and then we'll come back and do the committee questions, and we'll resume at that time. Thank you, everyone.
Thank you.
Okay, so we'll resume again at 2:50.